In this lesson, we're going to take a look at the cancellation technique. Now, the cancellation technique is often used to evaluate the limit of the quotient of two functions, like the limit as x approaches c of f of x divided by g of x, when the form 0 divided by 0 occurs. So to illustrate this, let's take a look at this example first. So we want to evaluate the limit as x approaches 3 of x squared minus 9 divided by x minus 3. Now notice this first. If you put 3 in for x into this function, you get 9 minus 9 divided by 3 minus 3, so you're getting 0 divided by 0. Alright, so what that indicates then is that this limit may actually exist. We don't know what it is, but it has a chance of existing. So what we're going to do is, let's rewrite this limit as follows. Now notice that the top can be factored as now you see that we have an x minus 3 in the numerator, and then the x minus 3 is in the denominator as well. So what we can do is cancel them, and so that's why this technique is called the cancellation technique. And what we end up with is, now this limit, of course, as x approaches 3 of x plus 3, that's just going to be 6. Right? You can just put the 3 in for the x. 3 plus 3 is 6. And that's your answer. So this limit, it turned out it did exist. And like I said, the 0 over 0 indicated that the limit may have existed. Now keep in mind that if we had put 3 in here and you ended up with something like 5 divided by 0, well, that would indicate that the limit does not exist. When you have a non-zero number in the numerator, 0 in the denominator, that would indicate right away the limit does not exist, and you could just write DNE. Now, let's see what's really going on here is this. X squared, because you can cancel up here, x squared minus 9 divided by x minus 3 is actually equal to this function. It's actually equal to the function x plus 3 when x does not equal 3, and it does not exist when x is equal to 3. So you see, this function is exactly equal to x plus 3 everywhere except when x is 3. Because over here we can't technically put 3 into this function. We get 0 over 0, which is an undefined quantity. But here we can plug 3 in here and we get 6. Alright, so that's why we ended up with this limit as being 6, because this function is really exactly like x plus 3 everywhere except exactly at the c value, which is 3 in this case. Now down here, if you take a look at this graph, this will explain it graphically what's going on. What you have here is, this is the graph of x plus 3. So x squared minus 9 over x minus 3 looks exactly like this graph, except you notice you have this little opening right here, this little hole in your graph, because this function technically does not exist at 3. So you have to actually leave a little opening right there. Now if you type this into your calculator and you graphed it, a calculator normally will not put a little opening right there. You would just see a straight curve going right through. But technically there should be a little gap right there. And if you look at the limit, if we let our x values down here approach 3 from the left and from the right, you'll notice that our function values over here approach 6. So just watch those function values on the y-axis. Notice how they are approaching 6 as x gets closer to 3 right there. And the same thing from the right hand side. Alright. So that illustrates what's going on graphically. Let's take a look at this example. Now if you want to, you can try this one on your own. You can pause the video here and try to evaluate this limit. Now I'm going to assume that you tried it already, so I'm going to go through the answer. Now let's notice first of all, let's notice if we plug -3 into the numerator and the denominator. If I put -3 in the top, I get 9 minus 3 minus 6. And then if I put -3 in the denominator, I get -3 plus 3, and of course we get the form 0 over 0. So that indicates this limit may exist. Alright, well, we will write this as and now you see the x plus 3's can cancel. So what we've done here is we've eliminated the problem part, which was the x plus 3. That was going to 0 originally. We've gotten rid of it. And so now this is just the limit. X approaches -3. And now you can just plug the -3 in for the x. And there's your answer. All right. Let's try this one. Here's another one. So down here now, we have this limit that we want to evaluate. Now this doesn't look like a polynomial in the numerator that we can factor and do any cancellation with the x in the denominator. Let's also notice this. If we put 0 in for the x here and here, notice that we get, and so we are getting that form 0 divided by 0. So this limit may exist. Now what we're going to do with this problem, it's not a polynomial to be factored, but we can do this. We're going to simplify the numerator by cross-multiplying or finding a common denominator. Now remember, when you find a common denominator or cross-multiply, when you add fractions like this, what you can do is multiply the a and the d, and then either add or subtract b times c, and then divide that by b times d. Right? So what you're doing is you're going AD, BC, plus or minus, and then multiply by the BD. That's exactly the same as finding a common denominator, that process, when you simplify fractions in that manner. So let's try that with this, and then we'll see if we can get that x to cancel somehow. So when we do that, this is going to be the limit. Alright, now cross-multiplying 4 times 1 minus x plus 4 times 1. Remember to put your parentheses around like that, so it's minus x minus 4. And then divided by 4 times x plus 4. All of that divided by x. Now, let's clean that up a little bit. The numerator up here, these 4's cancel, right? Because I'm subtracting that 4. I'm going to be left with negative x up there. And then in the denominator here, I can distribute that 4 if I want to, 4x plus 16. And then down here, we're going to have x. Now, because of the way this fraction is structured here, I can cancel these x's here. Right? Think of multiplying top and bottom by 1 over x if you'd like. Right? That's the same as just canceling these x's, and I get 1 and 1, and so this limit turns out to be the limit and now we can just plug that 0 in for x. We don't have any trouble anymore because we canceled the part that was giving us problems, the x, which was going to 0 in the denominator. And so we get our answer now as -1/16. And that's our answer. All right. So that's how we did that one. We still did some algebraic manipulation where we were able to cancel that denominator out, and then our limit ended up existing and equaling -1/16. Let's take a look at another one. Now here we have limit as x approaches 2, x cubed minus 8 over x minus 2. Now let's see, if we put 2 into both of these in for x in the top and the bottom, we get, of course, 2 cubed minus 8 over 2 minus 2, and of course that is equal to 0 over 0. So that indicates that this limit may exist. So we have to try to do some cancellation or manipulation somehow. Maybe we can cancel that x minus 2. All right, now I don't see immediately how x cubed minus 8 factors, but we do know this. X minus 2 is a factor of x cubed minus 8 because x cubed minus 8 is equal to 0 at 2. So that means x minus 2 is a factor of this polynomial up here. So we can do long division. So you have to brush up on your long division skills here with polynomials. Now remember what we want to do when we do this division. We want to knock out that x cubed right there by multiplying this by something. Knock out the highest power. So we're going to multiply by x squared. And so we get x squared minus 2x squared. Subtract. And so the x cubed, I'm sorry, this should be an x cubed right there. Apologize. All right, so the x cubes drop out, and we get, let's see, now we have no x squares up here, and we have no x's, so we're just going to get 2x squared minus 8 minus, there's no constant here, just minus 8. All right, now I want to multiply this by something to knock out that 2x squared, so we're going to multiply it by plus 2x. And when we do that, we get 2x squared minus 4x, and we are going to subtract that. The x squares drop out. No x's minus -4x gives me a 4x. -8 minus no constant, bring that -8 down. Now we want to get rid of that 4x right there. So I'm going to add 4 up here, because 4 times this term, that'll drop out the 4x's when I subtract, and I get 4x minus 8. And notice we get 0 as a remainder. All right. So that indicates that the x cubed minus 8 factors like this. So this limit is going to equal the limit as x approaches 2. And you notice those x minus 2's cancel now, and that was what was giving us trouble before. And now what we can do, so this is, let's rewrite it out. And now what we can do is just plug the 2 in for the x's because this is a nice polynomial. And our limit is going to be 4 plus 4, put the 2 in there, plus 4, and of course that is 12. And that is our answer. So that's how we had to do that one. We had to actually do some long division, and we recognized that because when we plug 0 into the numerator, when we plugged 2 in for x up here, we got back 0. That indicates that x minus 2 is a factor of x cubed minus 8. And so then we could perform long division, and notice we got a 0 remainder. All right. One more here, like this. So let's try this problem. In fact, I'd recommend that you try this one on your own. And I'm going to assume that you paused the video and tried it, so let's go over the answer. So, limit as x approaches -1 of this polynomial cubic divided by x plus 1. Now, let's notice if we put -1 in here for x, what we end up with is -1. -1 cubed is -1, plus 2, minus 3, plus 2, and then divided by divided by 0, -1 plus 1. And yeah, we're ending up with 0 over 0 here. All right. So what that indicates then is x plus 1 is a factor of this cubic polynomial up here. So if you don't recognize how to factor it right away, so we can cancel the x plus 1, then we're going to have to do long division. So x cubed plus 2x squared plus 3x plus 2 Alright, so I'm going to want to multiply this by x squared first. And subtract. Alright, notice how I had to bring down the 3x plus 2. Don't have any x or constant terms here. Then I will want to multiply this by x so that I cancel out this x squared. And now I will want to multiply this by 2. And notice that we get 0 remainder. So that implies that x plus 1 factors perfectly into that cubic polynomial. So then this limit is equal to notice how the cubic polynomial is now factored, and we can cancel the x plus 1's, which the x plus 1 here was giving us trouble as x went to -1, and now we have that this limit is simply and now we can just plug the -1 in for the x's. And that's our answer. All right. Let's take a look at this one. So, limit as x approaches 1 of x squared plus x plus 12 divided by x minus 1. Now, let's plug 1 in here and see what we get. See if we get our 0 over 0 form. Well, if we plug 1 in for x, we get, well, alright, you see what we're getting now is 14 over 0. So that indicates that we don't want to use the cancellation technique here. It indicates that this limit is just not going to exist. So we would just write then that it just does not exist. And we can see from the graph down here what is happening, Notice as x approaches 1 from the left, the function goes down to negative infinity. And as x approaches 1 from the right, the function is breaking upward towards positive infinity. And we can also see that from this graphic. Notice if I let the red dot, the x on the x-axis, as that approaches 1, the dot on the y-axis is the function value. That goes to negative infinity. As x approaches 1 from the left, and from the right, if I let x approach 1 from the right, the red dot on the y-axis goes to positive infinity. Notice how it just keeps increasing. Just went off screen. It's going up to positive infinity. So this limit does not exist. All right. And that concludes our lesson.